Today we will see what is line broadening mechanisms in the case of lasers. I will explain the classification of line broadening mechanisms and the reasons for each of these line broadening. The reference that you will have to use is Laser Fundamentals by William Silfast, which is the main textbook. You can also go through Laser Theory and Applications by M.N. Avadhanalu. Here I try to explain the concept of line broadening. Line broadening is basically if you can plot a graph of emission intensity as a function of laser wavelength or laser frequency, the spectrum that you are getting will be having a specific shape, and that shape is actually what we refer to as the line broadening. For example, if it is a perfectly monochromatic laser light output, just like in the case of laser, that spectrum will be a sharp line like this green line. If your emission spectrum is like this, intensity versus frequency or wavelength, if it is a narrow line, then that is referred to as a perfectly monochromatic light. But that is only an ideal situation, and no source is perfectly as monochromatic as this. But laser will come close. Whereas in the case of this red line, if the emission spectrum is like this, it is broader. Whereas in the case of black graph, it is still broader. So this in the case of this red one, there is less line broadening, whereas in this case the line broadening is very high. So basically line broadening refers to how many frequency components are present in the output or in the emission. If it contains only one frequency, then it is perfectly monochromatic, whereas in the case of laser, there is not many frequencies are not many frequencies are present in the case of laser output, so it is a very narrow line shape. Whereas in the case of LED, even though the emission is a single color, it will composed of closely spaced or adjacent frequency components will be there, so it will be slightly broader. Whereas in the case of a lamp, it will be composed of many frequencies and it will be very, very broad. So this is a simple explanation of what is line broadening. The classification of line broadening, it is broadly classified into homogeneous broadening and inhomogeneous broadening. We know that the emission is due to de-excitation of atoms from the upper level to the lower level. So emission is actually the result of the energy output due to the transition of an atom from the upper level to the lower level. So homogeneous broadening and inhomogeneous broadening, the classification is in such a way that in the case of homogeneous broadening, all the emitting atoms will equally contribute to the broadening. If all the emitting atoms can equally contribute to the broadening, it is referred to as homogeneous. Whereas if all the atoms are not equally taking part in the broadening mechanism, it is referred to as inhomogeneous broadening. So I will explain the concepts little bit more using this simple illustration. This is an example which I have used in order to explain a typical line broadening mechanism which is present in every system, which we call the natural broadening. Natural broadening is a homogeneous broadening mechanism. All the atoms will be equally affected by this broadening mechanism. So in order to explain this natural broadening, I have taken into account two energy levels, upper level and lower level, as in the case of the picture on the left side. So the energy levels are drawn to be like lines, which means the energy levels are very narrow. So the upper energy level and lower energy level, both levels are extremely narrow, or they are sharp energy levels. So when the atoms in the upper level de-excite to the lower level, the energy will be having a single, the output photon will be having a single energy, h nu, where h nu is equal to the difference between the upper energy and the lower energy. So correspondingly, if we plot the spectral line shape it will be a very sharp line like this. So that is one situation if the energy levels are extremely narrow. Whereas in the middle diagram you can see the middle diagram on the upper side I have drawn, instead of energy level I have drawn an energy band, the upper energy band and a lower energy band. So when the transition is taking place, an energy band is closely spaced sharp energy levels. So when we consider a de-excitation from the upper band to the lower band, I have drawn many arrows. All these will indicate possible transitions from upper sublevel to lower sublevel. For example, the first arrow, it is from the uppermost sublevel to the lowermost sublevel. So that will consist, that energy corresponding to this transition will be the highest, whereas the fourth arrow, it is a transition from the lowermost sublevel in the upper state to the uppermost sublevel in the lower state, and the energy corresponding to that transition will be the lowest. And in between, many possibilities are there depending on how many sublevels are present in each of these upper and lower bands. So that means when you plot the spectrum corresponding to the outputs due to this transition, it will be composed of many frequencies. We have got a central frequency, and on either side there will be many frequency components present. Therefore, in contrast to the first case, this one is a broadened emission. And if you are considering on the third diagram, the upper diagram in the third picture, I have drawn a still broader upper and lower energy bands. So that means naturally the transition corresponding to this upper band and the lower band, it will be composed of many frequencies, and it will result in a very broad line shape function. So this is the example. This type of broadening, it is actually due to the uh, energy level, broadening in the energy level, and it is referred to as natural broadening. Natural broadening is something which we cannot avoid because energy time uncertainty, just like just what you have learned in quantum mechanics, delta E into delta T should be a constant. So in the first diagram the energy levels are very sharp. The first diagram energy levels are sharp, which means delta E or uncertainty in energy is very low. So that means T, the next parameter is when you take the pair energy time uncertainty, the next parameter is lifetime. So when uncertainty in energy is very low, that level will be having extremely high lifetime. Low uncertainty in energy, which means high lifetime. So that means these atoms can stay there for a very long time. Lifetime will be very high, and the transition will result in very narrow emission line. Whereas in this other two diagrams, there is some finite uncertainty in energy levels, which means atoms cannot stay there for a long time, infinite amount of time they cannot stay there, so they will de-excite. But they will de-excite, and that de-excitation is spontaneous emission, which can take place at any instant. For example, if the lifetime of the upper level is 10 seconds, that means an atom which has gone to that level should de-excite within 10 seconds. And exactly at what instant we do not know. It can get de-excited after 1 second, 2 seconds, or whatever. But the thing is, it cannot stay there for longer than 10 seconds, where if 10 second is the lifetime. So when the energy uncertainty in energy is high, then the lifetime will be small, and so therefore the atoms will de-excite at any instant, and that will result in broader emission line. So that is referred to as natural broadening. So this is a general example or general explanation to understand how broadening is taking place in any system. Next we will see homogeneous broadening. In the case of homogeneous broadening, all the atoms, ions or molecules which are taking part in the de-excitation process and contributing to the emitted photons, they will all be equally affected by the line broadening mechanism. So all the atoms will be contributing equally to the broadened spectrum. And some examples for homogeneous broadening: first one is natural broadening, which I have just explained. In the case of natural broadening, it is due to the energy time uncertainty. If the energy levels are broad, it will be having a finite uncertainty in energy and therefore a finite uncertainty finite lifetime. And due to the finite lifetime, the transitions can take place at random instances, and that will lead to broadened output. And in this mechanism, all the atoms will be equally contributing to this type of broadening. The second one is an example of gas laser. In the case of gas laser, all the atoms or molecules will be moving and they can collide with other atoms, and due to collision there will be some change in energy, and that will affect the output frequency, and that will result in broadening. And all the atoms will be having equal chance of getting collided, so this will also be a type of homogeneous broadening, or collision broadening is a homogeneous broadening. And another example, third one, is in the case of solid state lasers. In most of the solid state lasers, we will be using crystal as active medium, and those crystals will be taken as a host material, and the emitting species will be doped inside. So these emitting species, which will be in the ionized state, will occupy some of the lattice sites. So they will be occupying similar lattice locations in the host material. So whatever broadening mechanism will be there, all the emitting species will be equally affected. For example, there can be vibrations in the crystal, there can be phonons which are propagating through the crystal, which will affect the emission. So whatever be the mechanism which can affect the energy of the output, all the atoms which are the active senders, or which are the emitting ions which are present in the laser medium, they will be located at identical locations in the host crystal. So whatever broadening mechanisms will be there, for example due to phonon, all these emitting species will be affected equally, and that will result in homogeneous broadening. We can use two mathematical functions in order to represent homogeneous and inhomogeneous broadened line shape function. For example, homogeneous broadening is represented by a Lorentzian line shape function, which is this blue graph, and inhomogeneous broadening is represented by Gaussian mathematical function, which is shown using this red graph. This is the Lorentzian line shape function, which is used for representing homogeneous broadening. This equation, y is equal to aw square divided by w square plus 4x0 minus x the whole square. It is a basic form of Lorentzian function. In this case, y is the intensity. For example, if you are taking the laser line shape function, y will be the intensity of the output, and x, which is the variable, it will be the frequency. Where so in the denominator, you can so this equation can be like I is equal to some constant into w square. W can be some function which is related to the time, or time constant in that broadening mechanisms. So w square in the denominator also. But what is important is this term, which is x0 minus x the whole square in the denominator. So if in order to identify the Lorentzian function, this is what we are looking for, whether we have got this kind of x0 minus x the whole square term in the denominator. So in the case of laser output, you have got, instead of y, you have got I, which is the intensity of the transition, or the intensity of the output. And on the right side in the denominator, instead of x0 minus x, you have nu 0 minus nu, where nu 0 is the central frequency and nu is all other possible frequencies. And a term like nu 0 minus nu the whole square should be present in the denominator, and there will be other constants also, which we will learn later. But this is a basic equation representing the Laurentian line shape function. This is used for representing homogeneous broadened transition, and the shape of the curve, you can see it will be identical with respect to the central frequency nu 0. So this is a homogeneously broadened line shape function. And in the second one is inhomogeneous broadening. In the case of inhomogeneous broadening, all the emitting atoms do not contribute equally to the broadened output, or all the atoms will be unequally affected by the line broadening mechanism. So that will result in inhomogeneous broadening. So examples for inhomogeneous broadening, for example, if you are considering gas laser, in the previous example we have seen gas laser can lead to collision broadening due to the movement of the gas molecules, and if the broadening is due to collision, it is all the atoms will be having equal chance of getting collided, so it will lead to homogeneous broadening. But in the case of gas lasers, there is another possibility of broadening is there. It is because the atoms in the gas molecules, it is not necessary that all of them will be moving with the same velocity. So when you have an emitting species, it will be emitting a particular frequency of a laser, a particular frequency of photon, but during the emission, the emitting species is also moving, so that will result in Doppler shift. So the Doppler shift will depend on the velocity of the emitting species. So since all the atoms are not moving with equal velocity, the Doppler shift will be different. So the frequency that, or the apparent frequency, or the frequency that we feel, will be different from each of these atoms. So that will result in unequal broadening. So that is one example for inhomogeneous broadening. But in the case of inhomogeneous broadening, this type of broadening is referred to as Doppler broadening. It is due to the unequal velocity with which the emitting species is moving, which will result in unequal Doppler shift, and that is referred to as Doppler broadening. In the case of inhomogeneous broadening, Doppler broadening is the major mechanism. Therefore, a Doppler broadening, the spectral line width is referred to as Doppler transition, or will be just like in the case of homogeneous broadening, whatever parameter that you want to represent in the case of homogeneous broadening, you will use a suffix h, whereas in the case of inhomogeneous broadening, we will be using d as the suffix, which actually stands for Doppler broadening. Why? It is because Doppler broadening is the major line broadening mechanism in inhomogeneous broadening. And another case is solid state laser. Previously we have seen in the case of solid state laser, all the emitting species are located at, say, identical lattice points, so they will be equally affected by phonons. But it is also possible that if there are defects in the crystal, then it is not necessary that all the atoms or all the emitting species will be located at identical locations, so, or identical lattice points. So that will mean they will be unequally affected by the transition phonons which are propagating through the medium. So that will result in inhomogeneous broadening. So these two broadenings which we have explained, the broadening in the case of gas and broadening in the case of solid state lasers. Broadening in the case of gas, there can be homogeneous broadening and inhomogeneous broadening. Homogeneous broadening is due to, in the case of gas, the homogeneous broadening is due to collision of the atoms. They will all be having equal probability of getting collided, and it will lead to homogeneous broadening. Whereas the same gas molecules, if they are moving with unequal velocity, they will result in unequal Doppler shift and will lead to inhomogeneous broadening. Similarly, in the case of crystal and solid state laser, if it is a perfect crystal that we are using, then all the emitting species will be embedded in identical crystal lattice points, and they will be equally affected by phonons, and that will lead to homogeneous broadening. Whereas if there are defects in the crystal, then it's not necessary that all the emitting species will be located with similar neighborhoods, so they will be unequally affected by the propagating phonons, and that will lead to inhomogeneous broadening. In order to represent inhomogeneous broadening, we are using a Gaussian line shape function, or it is a mathematical, the mathematical equation that we are using is Gaussian function. And I think you are familiar with Gaussian function. You can, in simple terms, you can represent it like this: I is equal to some constant into exponential. You have got a nu minus nu 0 the whole square term here also. In the case of Laurentian function, that will be appearing in the denominator, whereas in the case of Gaussian function, it will be appearing in the exponent. Okay, so this you have got some constants here and constant in the exponent also. They are related to the spectral width of the emission. The diagram of the Gaussian function, the graph of the Gaussian function can be represented like this. So when you're plotting the Laurentian function and the Gaussian function, you may probably feel that both of them are identical, but what is important is you have to plot these two functions taking the same omega and omega 0 values and same full width at half maximum values, and see which one is sharper and which one is broader. Then only you'll be able to compare these two functions. So these are the basic uh, theory that you have to learn in the case of line broadening mechanisms.